Okay, so a vector valued function. Continuing the theme of vectors. So vector valued function is a function that outputs vectors. Okay, so in general, a function just has an input and an output. A vector valued function is just a function that outputs vectors. And for us, for now, later we'll deal with other types of vector valued functions, but for now, we really want to think about the domain of the vector valued function just being the real numbers. And what we're going to see is that our conversations about vector valued functions are going to be almost identical to the calculus 1 and calculus 2 that we've already learned. And again, that's really because the domain of our vector valued functions are going to be subsets of the real line. And so we've already seen examples of vector valued functions. So we saw the vector equation of a line. That was an example of a vector valued function. You plugged in a value of t and you got a vector that pointed to specific points on the line. So in general, the form of a vector valued function is going to look like this. So we'll use our same vector notation, but we'll add in this argument t, and we'll typically use t for the independent variable, the input variable, because we really want to think in the back of our mind, vector valued functions are also giving us the position of a particle as a function of time. That's a good way to think about a vector valued function. So what we'll have is our output will just be, well, vectors, but each component is actually going to be just a regular function of one variable, and we'll just label them x, y, and z, and these will be called, so x, y, and z, these will be called our component functions. So they're the components of the vector, but they're actually functions of this one variable, t. Another nice way to think about vector valued functions is that they give, so a vector valued function, another just side note, maybe more of a technical note, we're going to assume that the component functions are, at least for now, continuously differentiable. And so that's just so that everything I say is going to make sense. And so a vector valued function another nice way to think about it is that a vector valued function gives a parameterization, so it parametrizes a curve. And again here, this is either in space or in the plane. And so of course we could have vector valued functions with just two component functions, x and y, if it was in the plane. If it was in space, it'll have 3 x, y, and z. And I already mentioned that vector valued functions can trace out the passive particles. They can also be thought of as giving parameterizations of curves. So just to nail down that last point about vector valued functions parameterizing curves, I just want to make the point clear of what is actually the output vector. Okay, so suppose we're in the plane, just to keep things visually simple. So this is the xy plane. Okay, and I'm going to trace out some curve like this. And I'm actually going to give the curve an orientation. So what I mean by that is, put simply, I'm thinking about this curve as being the position of a particle moving. So as t increases, the curve is going to be moving and increasing in this direction. So this is an oriented curve. And again, the oriented just means it has a direction. And so if I wanted to give a parametrization of this curve, so I would give some component functions. What are the actual outputs here? Well, for any given time t, r prime of t is just going to be the vector that's pointing to this point right here. So this is r of t, this vector. And so maybe over here, this is t equals 0. Maybe this is t equals 1. And then maybe this is t equals 2. So you see as time goes on, the particle is going to be moving along here. And then at any given time, my vector valued function is just outputting the vector that's pointing to where the particle is, like that. So I mentioned that because we're thinking about the domain of these vector value functions being the real line, that sort of the calculus we can do with vector value functions is very similar to just the calculus 1 or the calculus 2 that we did. And we'll explore that more in the next lecture. But for now, let's just note that suppose I wanted to take the limit as t approaches a of a vector valued function. Well, the nice thing about vector valued functions is that assuming all these limits exist, this is just going to be equal to the limit as t approaches a of the x component function. So that the limit is itself going to be a vector, and it's going to be the vector where each component is the limit of the component functions. And this is probably what you would expect in a situation like this. And similarly, so we can define limits this way. We can say that r prime of t, or r of t, is continuous at a t value, so it's t equals a, if the limit as t approaches a of our vector valued function is equal to just the vector that you get when you evaluate at a. Okay, so here's an example of our vector valued function, and we want to describe the curve that this vector valued function is parameterizing, and then we'll indicate with an arrow the orientation. And again, the orientation we can think about is the direction the particle is moving along the curve given by this vector valued function. Okay, so the easiest thing to do to find the curve is to try to write the Cartesian equation. So notice that y is equal to t, and x is equal to t cubed plus 1. And if we just plug in y for t, we have x is equal to y cubed plus 1. But now I can even solve for y in terms of x. So I can subtract 1 and then take a cube root. So I actually get y as a function of x. And now, hopefully you're all familiar with what the cube root of x looks like. And this is just a transformation, so it's shifted right 1 unit. So here's 1. And then my curve kind of has this S shape. that. So here's y equals cube root of x minus 1. So there's the curve that this function is parameterizing. And now I need to give an orientation. And I'll notice that both the x and the y coordinate are increasing as time, or t, goes forward. So my orientation is this way. So if this is the motion of a particle, it's starting down here and moving like that. Okay, so this is a really important example, and we'll see why in a second. So here's our vector valued function, and we want to see what the curve is it's tracing out, first of all. And so we want to try to write the Cartesian equation, and the trick is I'm going to use this identity. And it's probably the one identity from trigonometry I would say you should never forget. That cosine squared t plus sine squared t equals 1. It's more or less just a statement of the Pythagorean theorem. Okay, but if I look here, so here's x, and here's y, both of those as functions of t. Notice that if I take x and divide by a, and then square it, that's cosine squared, and I take y and divide by b, and then square it, I get 1. And here, of course, I'm using the fact that a and b are strictly bigger than 0. And so what is this the equation of? It's sort of like a circle. It's a little bit more general than a circle. This is actually the equation of an ellipse. Now, to answer our question, we'll go ahead and answer it. What is the curve when a equals b? When a equals b, this is, in fact, a circle. A and b give sort of the radii of the minor axis and the major axis of the ellipse. So you can think about an ellipse is like a circle, but it has two different radii. So let's actually sketch an example. Let's just take a to be 2 and b to be 1. Okay. And see what happens, because we also need to think about this orientation. So t is going from 0 to 2 pi. So what is this going to look like? Well, in the x direction, this a is telling me my x radius is 2. And then b is 1, that's like my y radius. That's 1 to minus 1. And then our curve is this ellipse that I'm going to try to carefully draw, not too poorly, like this. Okay, so there's our curve, the ellipse, and notice, just to kind of reiterate, this y radius is what we're saying is b, which is 1, and then this radius is a. Okay. Of course, when a equals b, it is in fact a circle, where I said that. So what about the orientation here? Well, when t is 0, we're at the point a comma b. A comma 0, because sine of 0 is 0, cosine of 0 is 1. So that means we're starting right here. And as we go up to, say, pi over 2, then we're going to be at the point 0 comma b, so over here. And so we see we're actually moving in this direction, this way. And we're going all the way to 2 pi, which means we're going all the way around the ellipse and then stopping back where we started. Okay, so here's another vector value function. And we now notice that this is in space. Okay, so already there's going to be a little bit more difficulty sketching this curve, and I'm going to limit kind of the amount of three-dimensional drawings I'm going to do because I'm not very good at them. But what we want to notice is that, okay, so this is x and y. So notice first that if we use our Pythagorean identity, we have x squared plus y squared is equal to 1. And so what does that mean? That if I just looked at the xy plane, I would be looking at a particle going around a circle. Okay, so in the xy plane, now the xy plane actually corresponds to z equaling 0. This is just a circle of radius 1, like that. But then, okay, so if I just look at the xy plane, I'm going in a circle. But what's happening in the z direction? In the z direction, I'm actually increasing with time. I'm actually kind of going up above the x-axis while I'm going in a circle. So what this actually is, so let me draw a basic three-dimensional coordinate system. This will be our first chance to kind of get our handle on that. So I'm going to put x over here, y over here, and z over here. Here's 1. And so I have this, I know that the, one way to say it is the projection onto the xy plane is a circle, like that, but I'm actually increasing. So if I take t equals 0, I'm going to be right here. I'm going to be moving around the circle, but at the same time I'm going to be going up in the z direction. So I'm going to be going around this circle, but at the same time going up in the z direction like that. And so this curve has a name. It's called a helix. And it's something that we'll just kind of mess around with for fun. It's a very interesting curve. It has some applications. And then we'll go ahead and mark the orientation. Because as t increases, z is increasing, we know we're going up the helix this way. And we already know that we're going around, sort of if we look at the projection, we know this is just going counterclockwise around the circle this way. So it's up like that. Okay, so now we're going to kind of be working backwards. We're given a curve, and we want to parameterize it. And I'll just go ahead and say this once, I'll probably say it again, that when you ask for a parameterization of a curve, end of question, there's more than one correct answer. There's nothing special about a circle, but there are different ways a particle can go around the circle. It can go around clockwise, counterclockwise. It's the same curve, but different parameterizations. And so sometimes the questions will be more specific, like in this example. We want a vector-valued function that parameterizes the following curve, a circle of radius 2 traced clockwise twice, starting at the point 0, 2. So the starting point plays a role, the orientation plays a role, the speed in which it's traced plays a role, the number of times it's traced plays a role. So there's a lot of things that play a role. So it's just something to keep in the back of your mind. So before we get into this, let's just recall that one parameterization of a circle is this. And this is for t between 0 and 2 pi. Okay, but This is tracing counterclockwise. Okay, so sort of by convention, cosine and sine increase with their arguments in a counterclockwise direction. And also from t going from 0 to 2 pi, that's only going to trace the circle one time. And the starting point is wrong too, because if I plug in t equals 0, I get 1, 0. And also, this isn't even going around a circle of radius 2. Okay, so there's a lot of problems here. So let me try to correct them. I'm going to do it all at once, but I'm going to kind of explain as I go. So first of all, to make the circle of radius 2, I need to double both of these functions. So 2, and then cosine. And I'm going to leave the argument out for a second, and 2 sine. Okay, so doubling those is going to allow me to go around the circle of radius 2. But how do I make the circle, how do I trace it clockwise? Well, I just want to reverse the argument. I just want to put in minus t. So what is that going to do? Well, instead of t increasing and going counterclockwise, t is going to be decreasing and going clockwise. Okay, but I also need to correct the starting point. Well, I'm just going to choose a different value of t. So instead, I'm going to start, okay, where's the point 0, 2? Well, that's going to happen when t is equal to 3 pi over 2 in this case, because when t is 3 pi over 2, cosine of negative 3 pi over 2 is 0, and sine of negative 3 pi over 2 is 1, times 2 is 2. So I'll be starting at the correct point. Okay. And then I want to go around twice, which means I want t to run through not 2 pi radians, but 4 pi radians. So 3 pi over 2 plus 4 pi is where I want to stop. Okay, and then that's going to be the parameterization that I get. And just take some time to think about everything that we did. We made it a circle of radius 2 by just doubling sine and cosine. We reversed the orientation by making the argument negative. And then we made it go around twice by just adding in another 2 pi. So instead of just going over an interval of length 2 pi, we went over 2 periods, and then we shifted our starting point to make us start at the point 0, 2. And now for B, this is actually a really important example. And we'll come back to this again and again. So we want to parameterize the line segment between 2 points. It just happens to be 1, 4, 4, and negative 1, 2, 1. And so the idea of how to write this parameterization is coming from the midpoint. So think about the midpoint of the segment connecting these two lines. Well, the midpoint is going to be this point plus this point divided by 2. So let's say this is point P, and this is point Q. So the midpoint is just going to be P plus Q over 2. And we can sort of extend this reasoning to get any point on the segment. If I'm over here, I want 100% of point P and 0% of point Q. But in the middle, I want 50% and 50%. And maybe here, I want 25% P and 75% P and 25% Q. So the way we do this parameterization of a line segment, it's also called a convex combination. So what we do is we take the point that we're starting from, 1, 4, 4, and notice I'm writing it in vector notation because I want the vector pointing to that point. And I'm going to multiply it by 1 minus t. And what this is going to do is when t is 0, I'm just going to get 1 times 1 comma 4 comma 4. But when t is 1, this point is going to contribute 0 to the combination, because I'm going to have 1 minus 1 is 0. And then the other term is going to be the other point, or more specifically, the vector pointing to the other point times t. Because now when t is 0, this point contributes 0. But when t is 1, this is the only point that is contributing to the combination. And then, of course, we want t to be in between 0 and 1. Alright, so we want a vector-valued function that parameterizes the intersection of this cylinder. And we're going to talk about surfaces a little bit later, but this is a cylinder because, well, you're lying on the circle of radius 3, and you're lying in a circle of radius 3 in every cross-section, no matter what z is. So that's exactly what a cylinder is. So we have x, y, and z, and here's our circle of radius 3. That. So here's z equals 0, but at z equals 1, it's exactly the same thing. And no matter what z is, we get exactly the same thing. So we're just getting this sort of infinite cylinder like this. That just goes on forever for all values of z. Goes up like that. Okay, so x squared plus y squared equals 9 is a cylinder. But then we're kind of cutting it with this surface z equals xy. And we really don't need to visualize right now what's going on, because all we're doing is we're trying to give just some vector value function that parameterizes the intersection of the cylinder. And the key thing to realize is that x and y are lying on circles of radius 3. So I can let x of t just be 3 cosine t, and y of t be 3 sine t. And you see that then x squared plus y squared will be 9. So now it's just a matter of figuring out what z is. But z is just x times y. So x times y is 9 cosine t times sine t. So my function is going to be 3 cosine t, 3 sine t, and then the z-coordinate will be 9 cosine t times sine t. And now there's going to be more than one parameterization. For instance, I can make my parameterization circle this intersection curve multiple times. But if I just want to circle it once, I'll just let t go from 0 to 2 pi. And that'll circle this intersection curve with the surface exactly one time. Alright, so we want to find the limit of this vector value function. But as we mentioned in the lecture, to take the limit of the vector value function, we just take the limit of each of the component functions as t approaches, in this case, 0. So we just want to take the limit, so the x coordinate is just going to be the limit as t approaches 0 of sine t over 2t. And I mean, this is just straight Calc 1. I mean, if you try to plug in t equals 0, you get an indeterminate form. But the nice thing is we've learned enough Calc 1 that we don't have to really think too hard about this. Let's just use L'Hopital's rule. So if we apply L'Hopital's rule, this is equal to the limit as t approaches 0 of cosine t over 2, which is equal to 1/2. And then in the y-coordinate, well, this is easy. This function is continuous at 0 for t, so we just get 0. So the limit as t approaches 0 of our vector valued function is just 1/2 comma 0. So this is just more Calc 1 review. So to take the limit as t approaches, in this case -1, we just want to take the limit of each of the component functions. So we want the limit as t approaches -1 of t squared minus 1 over t plus 1. We want the limit as t approaches -1 of square root -t minus 1 over t plus 1, and then same thing for the z component function, log of minus t over t plus 1. Okay, and all of these can be solved using L'Hopital's rule. You don't have to use L'Hopital's rule, but that's kind of the name of the game at this point. I mean, you have this really powerful tool. Why not use it? So I'm just going to tell you what I get. So here we get -2, here we get -1/2, and here we get 1. And so the limit as t approaches -1 of this vector valued function is just the vector -2